Hello, everyone. Thank you for joining us in Room 2 for the Big Mountain Data and Dev Conference. We will be starting with the presentation on serving very large number of machine learning models by Manoj Agarwal from Salesforce. If you have any questions, feel free to raise those questions in Loudswarm using the Slido widget, or you can use the Slack channel BMDD Room 2 for posting your questions as well. Thank you. Manoj, over to you.
All right, thank you, Anurag. Hi, everyone. In this session, we'll be talking about serving very large number of machine learning models. And this is who I am. My name is Manoj Agarwal. I work as a software architect in the Einstein platform team at Salesforce. This list, here are multiple ways you can reach out to me. I'll also share the same slide towards the end, so you don't have to note down this right now. First thing first, as Anurag mentioned, Slack channel and Slido are the ways through which we will be taking questions. So if you need an invite to the Slack space, here is the link for that. And after you're on Slack, please join BMBD_room2. That's where we are. And if you post any questions there, we'll answer those. And feel free to keep posting questions throughout the presentation. So first thing first, what is the problem that we are trying to solve, and some background on that. So Salesforce offers a platform called Einstein. It's a machine learning platform. It's a platform that allows CRM offerings of Salesforce to become intelligent. So just to give an idea of the use case, so Salesforce at Salesforce, people actually manage their sales data, marketing data, service data, all of the different kinds of data, and at times they might want to have some kind of predictions coming from the system. So, like for example, if a customer wants to know how many of their customers are going to pay their invoices on time this month, and that's a prediction that they want they want to know. So instead of guessing, they can actually ask this question from Salesforce Einstein. And behind the scene, Salesforce Einstein will go and create a machine learning model out of the data that customer has, historical data, and based on that model, it will predict on the current set of data, and it can tell with certain accuracy how many of the customers are going to pay invoices on time. So you can plan your budget accordingly, for example. So and that's just one example. There are like these predictions, they can vary from business to business, domain to domain, and customers can create multiple of these predictions. So roughly, Salesforce has customers in the order of multi 100,000, like about between two to 300,000 customers. And this Salesforce Einstein functionality is available to all of those customers. Now they have different kinds of offerings, like for free, I think you can create one or two predictions, but for the paid customers, you can create more. So as you can imagine that number of predictions that we make would easily run into billions, because there are that many customers and every customer has so many predictions. So this means that, and another dimension is that when Salesforce is creating that prediction, it's actually training a separate machine learning model for each customer, for each prediction, using only the data of that customer. Like we cannot, of course, use, let's say, Pizza Hut's data to train a model for Domino's and serve predictions for Domino's, right? So every customer has its own data that's separate, and their machine learning models are also separate. So now we have a huge problem on how to train that many number of models and how to serve that many number of models at scale. So that's what this presentation is going to be talking about. So more than a machine learning talk. It's, I would say, more of a distributed systems slash scaling talk. So just to set the expectations. So before we actually go learn about what exactly this model serving thing is that I'm talking about, let's look at the big picture. So a machine learning system, machine learning involves at a very high level these three steps: feature engineering, model training, and model serving. And we'll look at each of these three in detail in upcoming slides. So feature engineering, for example, it's about collecting data from various sources. So before you go creating any predictions, you would collect data that will help you come up with that prediction. So that data could be living in some kind of a data lake that your company has created, or it may be coming from various disparate data sources. Then this data goes through a data cleansing process where you need to deal with missing data, incorrect data, or outliers. You filter rows, you normalize columns, and after you have identified, after you cleanse the data, then you need to identify what are the columns or what are the pieces of data that are relevant to your prediction. So that is the feature selection and extraction part. And finally, you have the data on which you are ready to predict. After the feature engineering part comes model training. So model training involves defining a model. So when by defining a model means you're coming up with a machine learning algorithm, you're picking an algorithm. There are many different algorithms available for different kind of situations. So depending on the type of prediction that you're trying to make, you will pick one of the machine learning algorithms. You'll specify its parameters, or also called as hyperparameters, and then you provide the data that you have collected in the previous step, and you run a training job, model training job. Now, this model training job, based on the parameters that you have set, it will produce a model. You run this model against some test data set, and it can tell you how accurate the model is, how accurately the model is able to predict the values. If you're satisfied with the accuracy of the model, you're good to go. But if you're not satisfied with the accuracy, then you tweak the parameters and tweak the data that you're using for training the model, and you rerun the training job. So there could be many different iterations involved here. And sometimes these iterations are done manually. A lot of times these iterations are done by the machine learning framework that you're using itself, and the frameworks can auto tune. So, but after the whole model training process, you get some kind of a model. So with this model, now you can provide it some like actual data, production data, live data, and using that it can produce a prediction. So that's the part that is called model serving. Uh, Getting some data and based on using the model to come up with a prediction, that is the model serving part. So now going back to the Salesforce example, where we had hundreds of thousands of customers and millions of models. How do you serve all of these models at that scale through this model serving process? And model serving is not just it's not just as simple as using one model. It can be, but often it involves a good deal of business logic. So there could be multiple models that you are evaluating. There could be feature lookups that you need to do while evaluating the models. So all of that logic is bundled together as a serving flow or serving logic, and it's often actually exposed as a web service, some kind of web service that can be invoked from your applications. So that's the focus of our talk today. How do we serve multiple. Actually, when I say multiple, it's like a huge scale of models, hundreds of thousands of models or millions of models through a web service, while also maintaining low latency. So now that you know what model serving and what model
Hey
serving is
Manoj,
and where it fit.
Hey Manoj,
Yes.
it seems like there's some issue on streaming with Loudswarm. So I'm working with support to get it started. Maybe give it a pause for the few minutes till the
Okay.
Loudstorm stream resumes.
Okay.
Okay.
Do we need to restart?
I don't know. I will know once the
Okay.
stream resumes. Yeah.
Got it.
Sorry about this. I'm I'm asking support on the side
Yeah, no problem. Thank you
when
so
will
much
it
for
come live.
doing that. Yeah.
Okay, so we seem to be live now. It seems we had some technical issues to start the session. Manoj, I think it's best if you can start from beginning because I see
Okay,
it's on your current slide now.
sounds good.
Apologies to the audience who are in the session.
All right. Thank you, Anurag. So are we good to go now?
Yeah, I think if we can start from beginning, yes.
Okay. So it seems we lost about 20 minutes of the presentation. So I'm going to be very cautious of the time. But if you have any question along the presentation, please keep them coming. I will try to address as many of them as possible. So hi everyone. In this session, we'll talk about serving very large number of machine learning models. My name is Manoj Agarwal. I'm a software architect in the Einstein team at Salesforce. Here are various ways you can reach out to me, and I'll share the same slide towards the end also if you need to note some of this down. So first thing first, we'll be taking questions through the Slack channel as well as from the Slido platform. If you do not have an invite to Slack space yet, here's the link, and we are in BMBD underscore room 2 channel. So Einstein is Salesforce's comprehensive AI platform that provides a complete managed solution to the customers. Customers don't need to be an expert in machine learning to use Einstein. And this machine learning platform is integrated with almost all of the Salesforce products. Currently, we power billions of predictions per day. But this presentation is not about trying to sell you Einstein platform, but to share our knowledge and experience building this platform, specifically the model serving part. So what is model serving? Uh, Model serving is part of the bigger machine learning platform. Broadly speaking, a machine learning process involves three parts: feature engineering, model serving, model training, and model serving. So let's talk about each of these parts specifically. So feature engineering is about collecting data from various data sources. Data could be coming from a data lake that your company might have set up, or various disparate data sources. This data goes through a data cleansing process where you need to deal with missing data, incorrect data, and outliers. And to there are various ways to do that. You can filter rows, you can normalize columns. So there are various ways to clean the data to make it ready to be used for any kind of predictions. After that, you identify what columns are relevant to the prediction that you're trying to make. This might involve joining multiple columns or deriving features from multiple columns. So that is that feature extraction and selection part. After you have done your feature engineering, you've identified the data, then comes the next step, which is model training. So as part of model training, you come up with a model definition. This model definition includes like what kind of machine learning algorithm do you want to use, and that depends on the nature of your problem. Then you specify parameters for that algorithm, also known as hyperparameters, and using that the data that you prepared in the feature engineering phase, then you run a training job. This training job produces a model, and you validate the model against some test data set. With that validation, you figure out how accurately the model is predicting the values. And if you're satisfied with that accuracy of the model, then you have a model, you can use it. But if you're not satisfied, then you tweak the hyperparameters, tweak the data also, like maybe pick different set of columns, and then retrain the model. So this is an iterative process. Some of this iteration some of the parts can be automated, but often it's more of an art than science. So people, data scientists, they actually go through this process iteration until they are able to get a model that has very high accuracy, very high accuracy of the predictions that it's able to produce. So once you have the model, then comes the model serving part, and that's the kind of focus of this talk. So in the model serving part, it provides the predictions using the model. So you need to host that model in some kind of a web service. That's how people typically serve models. And model serving can be as simple as just getting prediction by evaluating a simple, just one single model. But often there is a complex business logic also involved where you are chaining multiple models or you are doing feature lookups from some data store. So all of that logic goes into your model serving service, or also known as prediction service. So this talk is about how do you scale that prediction service. So now you know what model serving is at the high level and where it fits in the machine learning process. Let's talk about the problem that we are trying to solve. So Salesforce has several 100,000 customers, and each customer can define one or more predictions on their data. So just to back up, to explain what is a prediction that I'm talking about. So let's say some customer is using Salesforce to keep track of their business process, and this month because they need to do their budgeting accordingly. So one way to do that is they can look at their historical data and make the guesses themselves, or they can ask this Einstein system that we have that's integrated with the Salesforce products. They can ask this system to make the prediction for them. So they will pick the relevant data columns, and they will ask the system to predict the invoice date, or if the customer is going to pay that invoice on time or not, that kind of column, just a yes no kind of a prediction. So that's the prediction that I'm talking about. So now each customer can define one or more of those predictions on their data, and each prediction requires one or more models. So to serve our customer predictions, this prediction service needs to be able to host several hundreds of thousands of those models, and those models need to be loaded in memory to be served. So we don't so that's the challenge that we're dealing with here. Uh, but we don't necessarily need to keep all of these models in memory all the time. So there is some kind of a trade-off. So I mean, we can load these models from disk on demand, but that also involves latency. So we need to figure out how do we reduce this cold start time or loading time from the disk and be able to serve a large number of requests for model predictions right from memory. So that's I'm going to share some of the techniques that we use to basically achieve that goal. So here are the requirements of a model serving service. I'll also refer to this service as a prediction service. So first thing first, it should be able to host a model and predict, right? That's the core functionality of this service. Then there are many machine learning frameworks available like scikit-learn, AutoML, TensorFlow, etc. And each of these frameworks have their strengths. So data scientists actually like to use different frameworks for different prediction needs. So this prediction service needs to be able to support multiple machine learning frameworks and multiple versions of those frameworks as well. So that's the next requirement. Uh, Next one is our service should be able to support multiple versions of models. So models themselves are regularly retrained to take advantage of the newly available data, and each new training iteration produces a new model version. So to support canary deployments, gradual rollouts, or A/B testing, this prediction service needs to support multiple model versions as well. And as we discussed before, we need to serve these hundreds of thousands of models with as many as possible from memory. So let's see one by one, how do we address these requirements? So first thing first, here we have the prediction service, then that has, for example, an AutoML container, and we have a model store that could simply be, let's say, S3, where we store models, and on receiving the prediction request, this service downloads the model from S3 and serves the request. So with just this simple setup, we have a prediction service that can predict. So our first requirement is met just with that simple setup. Our next requirement is to be able to support multiple machine learning frameworks and multiple versions of those frameworks. So how do we do that? So now our setup needs to be a little more complicated. So to support that, we need to host multiple different kinds of containers. Here I'm showing you an AutoML container, a TensorFlow container, and a PyTorch container, and a router component that, depending on the request, can route to different containers. Each container works the same way. It downloads the appropriate model from the model store and serves the request. So same concept actually we can extend to support multiple versions of the frameworks. So maybe we can have different containers like for AutoML 1.1, AutoML 2.0, different set of containers, and router is determining where to send the request based on the request parameters, and that way we are able to support multiple frameworks and multiple framework versions within one prediction service. So that kind of addresses my second requirement. Our next requirement is to support multiple versions of each model. So how do we do that? So to solve that, let's introduce a version management service. This version management service keeps track of the model versions and determines which version is the default version for each model. So let's say we have a V1 of a model running in production, and we trained a new version V2. And now we want only 5% of the traffic to use V2 while 95% continuing to use V1. So we should be able to configure that in this version management service. So it tells 5% of the requests, incoming requests, to use V2 version of the model, and rest 95% to use V1 of the model. So these requests, they carry themselves the information about what model do they want to use, and the request lands to uh, one of these clusters or containers, and they download that appropriate model from the model store if it's not in memory. So with this, we can, with the introduction of that version management service, we can support multiple versions of each model. Now next, let's figure out how do we reduce the latency. So far we have been actually downloading all the models from model store. And so in order to reduce latency, we can add caching layers in front of all of these IO interactions. So first thing first, we have an interaction from the router to the version management service. Maybe there could be a caching layer there too. Then for the models, we can add multiple layers of caching. We can mount a shared file volume to the serving nodes. So after we read first time from S3, nodes can directly read from the disk. And then we can have in-memory LRU cache on each of these nodes. And models can get loaded on first request, and subsequent requests can be served from memory. So caching is a very effective technique to reduce latency in this case. Now, the most complex requirement is scaling the system. So we need to scale on two dimensions. On these two dimensions are like scaling on the large number of prediction requests, RPS, requests per second, and as well as being able to support a large number of models. So how do we do that? So to scale for RPS, we can run multiple instances of each of these services and balance the load. So pretty standard technique that you can that you apply to any distributed system, not just the model serving system. So here I'm running multiple instances of the router service and multiple instances of the serving containers. Now let's consider one of these serving containers. So I'm just going to zoom in into this AutoML 2.0 cluster. So if we so here what we're doing, we are receiving a request. Let's say we are only zooming into AutoML 2.0. We are receiving requests and we are sending the request to one of these nodes in this AutoML 2.0 cluster. So if we have a standard load balancer does some kind of like either round robin or randomly load balances the requests among these nodes. So in that case, we pay the cold start penalty whenever model is loaded on each of these nodes the first time. By cold start penalty, I mean the latency that's involved in downloading the model from the model store to file share and from loading from file share to memory. So uh, whenever the first request comes to any of these nodes, they have to load the model in memory, and that involves that cold start time. So if let's say this cluster is made up of tens of or hundreds of nodes, we'll have to keep paying that cold start latency whenever the request is the first request coming to that node for that particular model. So as an optimization, we can do some kind of a consistent hash based routing. So requests for any particular model always go to one or a set of specific nodes. So in a way, we are actually sharding the models across this serving cluster. So this sharding allows us to scale linearly for serving a large number of models. So let's say one of our node can serve, let's say, 1,000 models, and we need to serve 100,000 models. So we can actually deploy 100 of these nodes, and they can actually nicely shard these models across that cluster of 100 nodes to serve 100,000 models. So with this, we have actually with this technique we can scale on number of models. Uh, Now we can also replicate the serving nodes itself to linearly scale for the number of requests per second. So now let's say each of my node is serving 1,000 models, and let's say each node is able to serve with certain RPS. If I receive more load, then I can just replicate that node and be able to serve more number of requests coming for the same set of models. So with this, I mean, we are able to kind of solve the linear scaling problem for both RPS load and the number of models. But then there are other issues that crop up at that scale. So a couple of those issues are noisy neighbor problem and hotspot. So if one model becomes overly popular or is heavily used, then it might affect all the other models that are co-located on the same serving instances. So to solve that problem, instead of consistent hashing, we can use a technique called shuffle sharding. Shuffle sharding, actually, you can learn about that online. There is a nice article about it on the in the AWS Builder library. In a nutshell, shuffle sharding distributes the models more randomly and minimizes the impact of a heavily used model on other models. And to implement shuffle sharding, we need to maintain a config map. So it's not a consistent hash-based sharding that you can figure out based on by running a formula. Now you need to keep a map of which model is hosted in what node, and with that, every time like a new request comes up, you refer this map If you find an assigned node, you go to that node. If you don't find an assigned node, then you basically work with that shuffle sharding algorithm to find the node assigned to that assigned to your model, and then you always send the request to the same set of nodes. So another one was hotspot. So with this config map, actually hotspot, the problem was that it's not just that my model is affecting other models that are co-hosted, but what if my model is overly popular and I'm receiving a lot of requests for that one model, but rest of the models are not that popular. So so that becomes a hotspot in my system, right? So how do you solve that hotspot problem? We can actually use the same config map to solve it. Essentially, what we need to do, we need to scale each of these models differently depending on the traffic that we are receiving. So let me just check the time. We still have about 20 minutes left, so that's good. So here we can collect metrics about the model usage, and based on this metrics we can feed it back to the config map, and config map can use that information, it can use the information of what model is used heavily, what model is are not used that heavily, and based on that it can figure out how much does it need to scale each model, and that it can do separately. So a heavily used model may be replicated to 10 different hosts, while a less heavily used model can be replicated to just 2 nodes. So with this, we are able to actually solve all of these problems. So this is how we implement all of these model serving requirements to provide a scalable AI solution for Salesforce. And that's all I had in my presentation. So thank you so much for attending this session. I hope you learned something. Feel free to reach out to me through any of these means. And if you have any question, we are open to take that.
Thank you, Manoj. If you have any questions, please use the slider widget on LoudSwarm, or use the BMDD Room 2 channel to post your questions.
Cool. We'll wait for a couple of minutes, and uh, if not, you always feel free to send me a message on LinkedIn, Twitter, or email me, and I'll be happy to answer those questions. All right. I think that's a
Thank
wrap.
you.
Yeah. Thank you, Anurag. Yeah. Everybody enjoy the rest of your conference.
Thank you.